Today, we're going to start with looking at some octahedral complexes and how we can look at the differences in color and come up with a justification of why and how we can relate this to absorption energy and something that we're going to call crystal field splitting. So in terms of the complexes that we were looking at the other day, we have CrF6, which has a 3- charge, and the color to our eye is green. If we also look at CrH2O6, this complex has a 3+ charge, and it's violet. We can continue to change the ligand and make this chromium complex with 6 ammonia ligands. Again, this is going to be 3+, and the color we see to our eyes is yellow. And then the last complex we can make with chromium is CrCN6. This has a 3- charge, and this has kind of like we'll call a faint yellow color. And this chromium solution is almost clear, but it kind of has this yellow tinge to it. And we'll talk about how that kind of affects the absorption spectra that we might see. So all of these complexes have chromium 3+ as the transition metal center, and all of them are in an octahedral environment. One of the other things that I want to look at is if this is a green color to our eyes, we have to look at the color wheel and figure out what the complementary color is, and that's the absorption that we're going to observe. So if we have a green compound, we're going to absorb light that has a red wavelength. If we have a violet compound, we're going to absorb yellow wavelengths of visible photons. If we have a yellow compound, the absorbance is violet. And if we have a faint yellow color, we're going to have a small violet absorbance. And I'll kind of touch on that here in a bit. So these are the absorbance colors. And basically what we can do is we can come up with some type of theory or some type of reasoning for when we change a ligand, what happens to the absorbance, and how are we analyzing that? We talked about how when we have an octahedral environment, how the d orbitals split. It turns out that when we change the ligand, we can have a different magnitude of that particular splitting. So if we set up an energy scale and we look at the d orbital splitting for each of these complexes, we have what we would call the triply degenerate or the T2G set of d orbitals here, and we have the EG set of orbitals. This is chromium 3+. In chromium 3+, we have 3 valence electrons, and those valence electrons are going to populate these orbitals to give the lowest energy configuration possible. So if I have to put 3 electrons in here, I'm going to put them all in the T2G set, and I'm going to make them all in the same spin direction. This difference between the T2G and EG orbitals we discussed as delta O. If we want to observe an excitation, that excitation happens from taking one of these electrons down here and exciting them up to here. This excitation energy is going to be corresponding to a wavelength of, in this case, with the fluorine ligands, it's going to have a red wavelength. And remember, red is next to the infrared region of the electromagnetic spectrum, and in terms of all the photons of visible energy, it's going to be the lowest or the smallest energy excitation. So the question then becomes, if I have fluoride as a ligand, and I synthesize this chromium complex and replace those fluoride ligands with, say, water ligands, we have something that's a violet color, which is going to have an absorbance corresponding to a yellow wavelength. So that absorption energy has to be greater because a yellow wavelength is going to be greater in energy than a red wavelength. So that tells us something about the relative splitting or the magnitude of the splitting in these particular orbitals. So if I have our T2G and EG set of orbitals for the water complex, if we're comparing it to the fluoride complex, we're going to put 3 electrons down here, and our absorption energy has a wavelength of yellow radiation. That also means that this delta O right here is going to be greater for the water complex than it would be for the fluoride complex. As we progress through and change the ligands to ammonia, we see the same exact thing happen, except now we have violet as our absorption energy, and the delta O is even greater yet, because violet is on the highest energy region of the electromagnetic spectrum, at least when we're talking about visible radiation. Same thing happens with the cyanide case, where we have an even larger delta O. And what we start observing here is that the maximum absorption, or this absorption band, keeps getting shifted over to higher energy when we go from a fluoride ligand to a water ligand to an ammonia ligand to a cyanide ligand. So we can come up, based on these experimental results, we can come up with some trends or some kind of a rule. And here's what we're going to say about this. We can say that when the ligand is changed from F- to water to ammonia to Cn-, the energies between the T2G and EG orbitals increases. And it's going to follow from this statement that since this energy increases, that the energy to excite an electron from the T2G to the EG also increases. So if we go from the ground state to the excited state, we're going to see an increase in energy here. Okay? This effect right here has a dramatic influence on the color. And I'm going to put in parentheses here, and magnetism. So how can we come up with a general rule that expresses this trend right here and also follows right along with the observations of these different colors?